Before we get started, I wanted to just take a step back and look at how far we've come. At first, we looked at something as complicated as language and saw that with a few simple rules called syntax, we can understand and recreate aspects of it. Then we saw that we can apply these same principles to things we already know and are familiar with, like arithmetic expressions, and even new things such as programming languages. Instead of just looking at an arithmetic expression or a line of code as a series of garbage strings of characters ordered in a meaningless way, we were able to see the structure it represents. Suddenly, the meaning comes from the chaos, and to someone from the outside, your ability to understand and manipulate these structures seems like magic. We then saw that recursion and induction are ways of making sense of self-similar structures, be it in a maths problem or a natural or programming language. You can build bigger things out of smaller things. We can apply this to something as daunting and complicated as learning a lot of the syntax of a new actual programming language. It was easy because we could reduce the whole task to understanding a few lines of syntax rules. Now that we could describe and manipulate syntax trees, we needed a way of stitching those trees together in a way that makes sense. So we used types. Types helped us figure out which pieces of the syntax jigsaw puzzle fit together and which ones don't. Once we could start putting these pieces together, we noticed that, hey, I'm repeating myself a lot here. Is there a way I can shorten this thing that seems to come up over and over again? So we stumbled upon abstraction of patterns and started building functions, little handy tools that help us put together patterns of pieces in a way that we've realized comes up often. We realized that functions can also use recursion and how to fix them if they go wrong. That's a lot. And there's just one more thing I wanted to cover before I move on to lists and all the wonderful problems you can solve with them. I'll try use an analogy of jigsaw puzzles to motivate where we've gotten so far and what the last step is. A natural language is like the photo on the box of a jigsaw puzzle. It's all one big thing, and it's good for getting an overview of what you're aiming for and thinking about. Syntax rules are like cookie cutters that you can use to split this picture up into different parts. Good rules will preserve the structure of the puzzle and make it easy to not only understand each piece on its own, but how it can fit together with other pieces. Bad rules can make it really difficult to figure out that structure again. When you want to build up a puzzle, you look for the small parts of the puzzle you can get started with. Those look like corner pieces, those look like edge pieces. Let's try solving that bit on its own. Those look like there's the same color. Maybe they go together to form this fruit in this image. Without even realizing you're using recursion, you're solving smaller bits of the puzzle independently, then recombining them with other pieces to solve bigger parts. Types can be thought of as the shape of a piece. Colors of the piece are like what the code does. If all the pieces look the same, you can have pieces that go together but actually have the wrong color, so you have to spend longer to try and figure out whether they actually match. If pieces have a really different shape, even if they have a similar color, then you know for sure that the pieces can't possibly fit together. The shape of a piece is a good way of checking that you're not too far away from the intended solution. It might take longer to find the piece that fits, but once you do, you know you're right. In this analogy, functions can be friends who are really good at a particular kind of problem. You might have a friend who's really good at edges and corners, so you hand them the pieces of the right type, the ones that look like edges and corners. You might have a friend who's really good at outlines or putting similar colored pieces together, so whenever you notice a pattern of pieces you think they can handle, you ask them to handle it. So as stretch, you can imagine that there would be some value to having some way of making your friends, who are each good at one thing, to work together to be good at something new, which uses and combines their skills to solve a bigger part of the problem. You're the one who has to make sure that they get the right pieces, and also make sure that the things they produce fit together. So this last idea, of taking just one more step out and abstracting over functions, is what we're looking at today. As always, What we're looking to do is notice patterns and replace it with something shorter. It's okay if it takes a bit of time to understand, but it will happen with enough practice, and then you'll wonder how you ever thought about programs without it. What I suggest you do is skim through this video once and revisit it every so often. Get the idea and trust that the details will sink in over time. Before the code, let's try seeing if we can get an intuition for manipulating functions visually, as diagrams. This is new for me too, so let me know if it's helpful or not, or if you have a different way of thinking about these things. Functions are sometimes drawn as boxes. An input goes in on one end and then something else comes out on the other. When I need to, I'll write the types of the input and output along the edges. In code, this will look like f has type A to B. Applying a function means connecting an input to the box and looking at its output. We'll connect an input to the function with a double arrow and the output with an equals. In code, we'll write it as x pipe into f or f of x. Some examples are 3 plus 4 equals 7, hello double plus world equals hello world, or x goes to x applied to 3 is equal to 3. Lastly, once we've applied a function, we can simplify the diagram by just keeping the output. The goal of this game is to make new boxes from the ones we're given. And in a sense, that's all there is to programming really. The difficulty is figuring out how and not repeating yourself too much. What we'll look at today is some really common ways of making new boxes from old ones that come up all the time. A really simple way to see this is to think about how we break down a problem. First we do something, then after that we do something else, and so on. To show this, we can have a box called after. It will take two boxes and make a new one out of them. Say we have f and g, and we want to chain those two boxes together. We want a new box that first does f and then does g. We can write it like this. Join up f, join up g, and then make a new box which has f and g inside them, joined together. And because we only want to join things up in a way that makes sense, like jigsaw puzzle pieces, we check that the edges match using types. And so in code, we would have after g, f is equal to x goes to x pipe into f pipe into g. Or using the old style, after is equal to g, f goes to x goes to g of f of x. If you've ever made a circuit, then this is just like joining up wires between different parts of a circuit. You may have seen this in physics as serial connection, and computer scientists like to call this sequential composition. This may make you wonder, is there a way of doing things at the same time? Joining boxes and functions up in parallel rather than in series? And the answer is yeah, there sure is, but with our box diagrams, there isn't a great way of showing this. Having two equal signs come out of a box doesn't really make sense. How can one thing equal two potentially different things? How can a function return two different arguments? The problem of a box only having one equals out is pretty easy to get around because we have records and tuples. So if we already have a box with two boxes f and g connected up parallel inside, we could write this diagram, which in code would look like f of x, g of y inside a tuple. Just as a box, it would look like x, y goes to f of x, g of y. So if we want to make boxes that work like this for our own choice of f and g, let's call it tuple, we can draw it like this, which in code would look like let tuple f, g equal to x, y goes to f of x, g of y, or tuple equals f, g goes to x, y goes to f of x, g of y. Again, we want to make sure that we only connect up pieces in a way that makes sense, so we use types. Remember that the bits in pink are just a syntax for writing types, whereas the bits in green are the types themselves. There's just one more thing to notice about this. We can look inside tuple FG and see that actually there's another hidden thing that it's using. If we write a very silly looking function called pair xy is equal to x comma y, then we can see that tuple is secretly using pair without telling us. So then a completely fair question to ask is, if we get to tell tuple what to use for f and g, why not make it use what we want for pair as well? So we could make a new box, let's call it parallel, which looks very similar to tuple, but instead of pair we get to choose what we do at the end. So we write let parallel fg rest is equal to rest of f of x comma g of y. And then to check our work, we write in the types to make sure all the pieces fit together. Now let's add one last restriction to the rules of this box game, and that is that boxes can only take one thing in. So to get around this, we could force everything to take in records and tuples, and that still works. But let's get imaginative. Say we only give one input to something like addition, plus, or double plus for strings. What should happen? What's a fair thing to expect? You could say that if I only give it one of the inputs, I want it to act like a new box. One that just waits for the second input and does whatever it was going to do with the input it had inside and the one it just got. So for plus, when we only give it 3, we want a new box, such that when we connect that box up, say with 5, it gives the same answer as it would have had we connected both the inputs 3 and 5 to the original box at the same time. So let's go over that again with double plus. When we connect up just highness, we want a new box. That new box has highness almost stored inside it, and that new box behaves just like the old one, except it always has highness as the first input. So if we connect up the string Ada to the second one, it should be the same as connecting up highness and Ada at the same time to the first one. Now, you could always do this in code by writing let address equals x goes to highness double plus x. But the neat thing is, you don't even have to give this a name. You can just write x goes to highness double plus x, or even highness double plus underscore, or highness double plus, as a shortcut. Similarly for before, we can write 3 plus underscore, or just 3 plus. Lastly, if you have 3 inputs, you can do the same thing. At each step, you're fixing and storing all the inputs you have so far. The surprise is that in Reason, x, y, z goes to something is just a shortcut for writing x goes to, y goes to, z goes to the same something. And conversely, writing f of x, y, and z is just a shortcut for writing f of x, of y, of z. Let's shift gears a bit back into code and look at a very silly example that will help you practice getting your head around some of these ideas. Say you're writing a function like let f equals x goes to x plus sin x times cos of x times x minus 3. But you get bored of writing out the x's everywhere. It's obvious what you'd mean if you just wrote sine minus tan. Why isn't that okay? Well, honestly it is, and we can do just that. First, we need a bit of setup. We need to define the identity, just, plus, minus, star, and composition, and square for functions. Then we can rewrite the above function as follows. Let f is equal to id plus sine times cos at square minus just 3. The real question is, why does this work? We can use what we know and write out what's going on. First, we rewrite the whole thing into a syntax tree. Now we take a very deep breath and start from the outside in, expanding each symbol as we go along. First we expand the plus and apply X to the left and the right. Then we expand the minus and again apply X to both the right and the left. We continue with star. Finally, we expand composition with the @ symbol and square to get the original function. We got a lot of practice applying things which look like they take 3 arguments to only 2. We're taking advantage of the fact that by not giving all the arguments to plus, star, minus, or @ we are making new functions that wait for the last argument. Now you should try it. Pause the video and do exactly what I just did, but try working from the inside out. It might be a bit trickier, but just take it slowly and I'm sure you'll learn a lot. This idea is called lifting. We take a function, like plus dot, of type float to float to float, and make it mean something different at different types, in this case at the type of functions. And it will come up a lot, especially when we start looking at even more patterns and concepts. Let's finish by looking at the example of derivatives. From maths, we know this rather boring looking definition of a derivative. F prime of a is equal to limit as delta tends to 0 of f of a plus delta minus f of a all over delta. We won't really take limits here, but if we do just 2 lines of code, let delta equals 1 dot e negative 6 and let deriv is equal to f comma a goes to f of a plus delta minus f of a all over delta. We can now write things like let f prime is equal to deriv of f, and more generally we can use the above approach and just say give me the deriv of sine times cos from before. Now this approach isn't actually used in real calculus code, but I think it's a really good example of higher order functions. You give deriv a function and it gives you back a new function, its derivative. You could even take the derivative again, so you say let f prime prime is equal to the deriv of f. So in summary, there's 2 things I want to end with here. The first is that if you think about functions as boxes, you put something in at one end and you get something out at another. Then you can make bigger boxes out of smaller ones. It just so happens that the process of turning these smaller boxes into bigger ones, you can also draw as a box. Sometimes you can do it with functions regardless of what they do, like connecting them up in serial, in parallel, or not giving them all their arguments up front. Sometimes you can only do it with specific kinds of functions. Our plus times star functions only work if their f and g arguments have the type float goes to float. The second is this: if you're feeling confused, or like that you get the high level idea but don't actually see how to use this or how any of this would be helpful, don't worry. Keep going with the rest of the videos and then come back to this one often. It will sink in eventually.